Hey there, team chemistry coach coming at you again. I got one of my gift from a student chemistry coach. That was just a nice gift. I love it. So anyway, we are going to be looking at some more lab stuff that you may have to do. This one being error analysis, which is the bane of every lab student's existence. Usually causes massive neuron damage, or they just don't like doing it because of the way that I teach it quantitatively. Most students want to look at error analysis qualitatively and just guess. But there are, there's situations where that works fine, but there's other situations where that doesn't work fine because of the way the mathematics set up. It's pretty much almost impossible to guess. And then you get wrong answers and you don't know why and you don't know how to approach it. So I want to teach you a way that works every single time. All right. So what we're going to do, there's two reasons for this. And you need to do this as a chemist. If you're running an experiment, let's say you have a true value and you have your experimental value and they're not the same. What happened? Maybe it's really bad. We'll call that a poor result, right? And maybe it's good, but not good enough in your book. And so a common question, if not the most common question I get when I'm teaching lab is, why, Professor, why did I not get the true value? I'm like, then I got to sit there and think about what they did in their experiment. Now, I can ask a lot of questions. Hey, did you do this? Did you account for this? Oh, you forgot to do that. You forgot to condition this. The reason your value is too low is because you accidentally added water to your solution. So maybe you made a solution, poured it into a container that had water, some water on the inside and diluted it down. And that's why your result was less than what it should have been, right? So this is all error analysis. What could possibly have happened to give an inaccurate result, right? So that maybe if we have time, we can go back and redo it, accounting for that, and then go, oh, okay, I fixed that error and I got a better result. Hey, there you go. And we want to be able to analyze things, but we wanted to be able to do it quantitatively to get a more accurate look at it. Or we could flip the tables on that and say, hey, we're about to do an experiment. So let's theoretically think about, hey, if this error occurred, let's say I screwed up and did this, would that give me an answer that one is an error? And if it is an error, would it give me a value that's higher than it should be? Right? So let's say this is the true value. If I made this error, would it give me a value that's too high, higher than the true value? Or smaller? Is it bigger than the true value or smaller than the true value? So you can analyze this ahead of time. You don't even need laboratory data to do it. We can just use fictitious numbers, throw them in there and just say, hey, this would be bigger or this would be lower than that true value. So what I'll do is I'll go through the steps on how to approach it. It really depends on the experiment. Each experiment is unique. You have to look at what are the measurements, what kind of calculations am I doing? How do they depend on those measured values? Right? Is that value in the numerator, the denominator? Am I subtracting it? Am I adding it? It changes the whole game. Right? So I'll list through the steps, and then we'll pick a specific experiment, and we'll work on the theoretical one, so we don't have to deal with actual data. But you'll do this all the time in lab. Hey, Lux, how did I screw up? I'm like, I don't know. I'd have to watch you do it, right? So let's do one where we theoretically predict ahead of time whether a particular error would give us a value that's bigger or lower than it should have been. Here's some steps for you. Not all of them. There's 6 of them, but I couldn't squish the 6th one in there, which is the most important step. We'll have to do that as a separate board. But in general, here's what we're going to do. For any particular experiment, we're going to identify all of the measurements that pertain to that experiment. Right? So measuring the mass of this or the volume of that or the temperature of that, right? So let's identify everything that is a measurement and label those, right? This can be done before the experiment's even performed. Let's label those measurements as, hey, measurement number 1 is A, measurement number 2 is B, measurement number 3 is C, however many measurements there are. Just label them, A, B, C, D. Now let's rank them based on size, right? So say measurement B is the lowest and measurement C is the second one, and measurement C would be the, D would be the heaviest if we're doing masses or volumes, whatever. So let's just rank them from lowest to highest. And then what we're going to do is we're going to assign an arbitrary value. Remember, we haven't done the experiment yet, so we don't have any numbers to assign to them. So let's just pick some fictitious, arbitrary, theoretical number, right? And we got them ranked from lowest to highest. So give the lowest one the lowest value and the highest one the highest value. Try to give a gap between them. Don't use like 1, 2, and 3, because then we're going to be altering them later. You don't want to alter it so then it, the lowest one still has to be the lowest one, right? So I like to pick numbers like, 20 or 25 and then 50 and then 75 and then 100, whatever. Doesn't not matter what numbers you put in as long as they correspond from lowest to highest, right? You'll see when we do this. So now we've got all our measurements labeled and we've put fictitious or arbitrary values in for them. Now let's look through the experiment and identify everything that's a calculation that's based on a measurement, right? Measurements are primary data. This is what we would write in pen in our labs. And then all the calculations would be called secondary data. We would use pencil in our particular labs. And what we want to do is take everything that's a calculation that depends on the measurements and set up an algebraic equation for how to calculate that particular value, that calculation. So say, we measure the mass and the volume, and then we calculate the density. Well, let's say the mass is A and the volume is B. Well, the density would be A over B, right? Or maybe we're measuring the mass by difference. So here's the mass of, say, an empty graduated cylinder. Here's the mass of that cylinder with some liquid. If we subtract those, that would be the mass of the liquid. See what I'm saying? So set up an algebraic equation for every calculation, whether there's one calculation or 2 or 3 or 4, it doesn't matter how many calculations there are. Set them all up as an algebraic equation in terms of the labels you assign to the measurements, right? Because we want to know, is that value in the numerator? Is it in the denominator? Are you subtracting that value or adding that value? It makes a huge difference when we do error analysis later. Remember, we haven't assumed any error yet. We're just setting up what I call a baseline. So we've got our equations. Without the equation, you're pretty much toast. You're just guessing. So I will always check that equation first. Now what we're going to do in step 5 is calculate a value for that calculation. We're going to determine if we had calculated, say, this density, we assumed a value for the mass, we assumed a value for the volume, and let's take the mass divided by the volume, say 100 divided by 50, that would give us a value of 2, theoretically. All right. And that would be a theoretical baseline value, assuming no error, right? Assuming a perfect experiment, which probably would never happen in the real world, right? There's always probably going to be some kind of error that happens. So in a perfect world, this would be what we would get in this experiment, theoretically, assuming no error. So now in step 6, which I'm going to have to put on the next board, that's when we're going to assume some error occurs. And we're going to have to identify, well, if this error occurs, which of our measurements, A, B, C, or D, or whatever, would that error actually impact? And then would that error cause that value, that measurement, to be higher than it should have been if there was no error, or lower than it should have been if there was no error? Right? And if it causes that error, then we're going to change the value that we assigned it. Right? Remember, we assigned arbitrary values, but now what we're going to do is assign a new value accounting for that error and recalculate everything and compare to the baseline and see if that number is higher or lower than the baseline. So let me get number 6 up here. We'll talk about that in a little more detail. That's where most people have issues in their brains. Step 6 is the complicated one. It's quite involved. Right? So what you've done is you've gone through, you haven't assumed any error yet, and you've determine algebraic equations for all calculations based on the measurements that you've assigned values for, assuming theoretically a perfect experiment with no error. So you've got these baseline values to compare to. So now for any error being analyzed, say this spills or that was overheated or it was weighed while it was warm, making it too light, whatever the error was, doesn't matter. You got fingerprints on it, etc., etc. For whatever error it is, so assign some error. Maybe your professor can assign some error. You can get together in small groups and brainstorm. Well, let's think up 10 different errors that could possibly happen with this experiment. And let's analyze whether that would give us a final value that's higher or lower than we should get, the true value. We want to identify for a specific error what measurement is affected. So say there's 4 different measurements you make. Well, that particular error will probably affect 1, maybe 2, but usually just 1 of those errors. All right, so this measurement was affected. Is it A, B, or C, or D? And then would that error cause that measurement to be smaller than it would have been without the error, or larger than it would have normally been without the error. Like I said, if you weigh something when it's warm, that's going to give you a lighter value than it should be. Buoyancy effect, right? Then what we're going to do once we've identified the measurement affected and whether it would be higher or lower, well, let's alter the assigned value. So let's say it affected measurement B, which we had assigned a value of 62 without the error. Well, if this error would make B smaller, well, instead of assigning 60, let's assign 50. Oh, and then recalculate the value of interest, right? But instead of using 60, use 50 and see how it changes your ultimate answer. And what you do is you compare that new value with the error included to the original baseline value, assuming no error. If you get a value with the error that's larger than the baseline value, that means that particular error would give you a bigger value, right, than it should be. So we can use, like, say, a capital B to say this would give you an error on the big side. It would give you, let's say our true value was, 0.52 grams. Well, this would give you, say, a 0.6 grams or something. It'd be bigger than what it should be. Well, let's say the value you calculate with accounting for the error is smaller than the baseline, assuming no error. Well, obviously that would give you a value that's too low or smaller, so we can use the letter S. That would give us a true value smaller than what it should have been. Well, sometimes, pretty rare, it'd be pretty boring, the value you get, assuming the error, is the same as the value from the baseline. Well, obviously that'd be no effect. That error could happen, and it would cause no difference in the final value. Oh, I guess it's mathematically possible, but not going to happen very often. You'd give it an N, no effect. Let's actually do one. Let's set up, what I'll do is I'll set up a fictitious experiment. Let's look at the measurements. Let's look at the calculations. Let's assign values and just walk through the steps together. We can do it. All right, let's say we just have some fictitious experiment we're going to do. Let's say we're going to, take some iron, heat it up, and convert it to iron oxide, rust. Okay? So obviously we'd be taking the iron and adding oxygen to it from the air. Let's say we take an empty, ceramic evaporation dish, weigh that, add some iron strips to it, weigh it again. We could subtract those to get the mass of the iron strips, the original ones. And then heat it up to form this gunky rust and stuff like that. Let it cool down to room temperature, weigh it again. So that's the mass of the evaporation dish plus the rust, the iron oxide. So we can subtract the empty evaporation dish from the mass at the end to get the mass of the iron oxide or the rust. So lots of things we could calculate from that. Well, let's do step one. Let's list up all the measurements. So let's take a look at what measurements we're having here, and let's label those A, B, C, D, etc., etc. All right? So based on looking at this, and it doesn't matter what order you put them in at this point. So we're measuring the mass, would you agree, of the empty beaker, or not beaker, empty evaporation dish. So let's put the empty evaporation dish here. So we weigh that, and then we're going to put the iron strips in there and weigh that. Let's do mass of dish plus the iron strips. So we have not heated it yet. We just added the iron strips. And then we'll heat it up and get the mass of the evaporation dish plus the rust. Right, the caked on, hopefully we have a high surface area for that iron so it reacts with the oxygen from air. So we really only got 3 measurements here. So let's just label things. Now we can even go lightest to heaviest if you want to here. We could combine step 1 and 2, but we don't have to. So it doesn't matter how you label these particular things. You just go A, B, C if you want to. I'm trying to find a color. I'm having a hard time. So let's just label this A. Label that B, and label that C. Whatever you want to do. You can call it XYZ. I don't care. The XYZ papers are affair. Let's do step 2. And a lot of times I'll combine step 1 and 2. I'll actually rank them from lightest to heaviest. I think we did that, right? Would you agree that the evaporation dish would be lighter than the dish with stuff in it? Oh, so that would be the lightest one, right? So we're going to rank. We're going to rank these measurements based on their size. So I'm definitely going to say the empty dish would be the lightest, correct? And then now we got to think, would the iron strips be lighter or the iron strips with the oxygen added to it? Well, when we heat it, we're adding oxygen, so it gets heavier. So it looks like the dish plus the iron would be heavier than the empty dish, but lighter than the dish plus the iron plus the oxygen, right? So I'm going to put the dish plus the iron here, and that would be less than the dish plus the rust, which is the iron plus the oxygen. Right? And so the empty dish was A, right? And the dish plus the strips is B, and the dish plus the rust is C. So now we can assign arbitrary values to these. And that would be step 3. So we'll do that on the next board. And it doesn't matter what you assign. This just has to be the lowest. That has to be the highest. So I could do like a 1, 5, 10, a 10, 40, 70, a 100, a 500, 1,000. I don't care what numbers you put in there. We'll just put some numbers in there. Usually I'll use the 100 range, like 30s and 50s. So assign whatever you want. I'll go on the next board and assign some numbers here. All right, let's take a look at this here. And again, you can assign any values you want as long as you keep them with the proper ranking. So remember, we rank the empty evaporating dish as the lightest, then the dish plus the iron is the middle, and the dish plus the rust being the iron plus the oxygen as the end. So I just said, let's make it 30, 50, and 80. You could have gone 20, 40, and 90. I don't care. It all works out the same. You'll get the same answers in the end, just different numbers, but you'll get the same answer saying this error would cause a bigger value, this error would cause a smaller value. Right? Now, step 4, let's set up algebraic equations for whatever parameter is being solved for. I never specified that in the problem. Let's say the purpose of this experiment was to determine the percent oxygen by mass in rust. All right, well, it could have been anything, but let's just say it could have been the percent iron. It doesn't really matter. But it would give you a different equation, right? But I just want to keep it simplified for this video to keep it lengthwise. Let's just solve for one thing. So we want to know what the percent by mass of oxygen is in rust, which is the iron oxide compound. Well, percent by mass is part over whole. The part of interest is the oxygen. The whole is the rust. So that would be the mass of the oxygen that we added to it, sucked out of the air, divided by the mass of the rust, which is the iron oxide. So we need to figure out what those are in terms of A, B, and C. Oh, this is where most people screw up. They get the wrong equation. If you got the wrong equation, all of your answers will be wrong. I've had students come in with all their answers, and every single one's opposite what I had. Like that. That's because you had your equation backwards. So let's figure out what the mass of oxygen and mass of rust would be. I thought the mass of rust would be easier, so I started with that one. The mass of rust, of course, we have rust here. So if we want the mass of rust, we just have to subtract out the mass of the empty dish, right? So let's take the mass of the dish plus the rust, subtract the mass of the empty dish. So that would be the mass of the dish plus the rust is C. The mass of the empty dish is A. So would you agree that the mass of the rust would be C minus A? Actually, we got to multiply this by 100. So let me do this over again. Let's times this by 100. Convert that ratio into a percent. So this will be C minus A on the bottom. And now let's figure out what the mass of oxygen is. See the thinking process? So the mass of oxygen, now none of these have oxygen directly. So we're going to have to think a little harder. Now the only thing that contains oxygen is the rust, right? The rust is the iron plus the oxygen. So we have to start with the mass of the dish plus the rust. So we have to start with C. Correct? Everybody agree? If you don't agree, think about it. Now, if we subtracted the dish, that would be the mass of the rust. We don't want that. We want the mass of the oxygen added. So if we subtract the mass, see, if we want just the oxygen, we got to get rid of the dish, the empty evaporating dish, and the iron. We have the mass of the empty evaporating dish and the iron. So if we take dish plus iron plus oxygen, which is the rust, right? Subtract the dish plus the iron, we're left with the oxygen. So if we subtract the mass of the dish plus the iron from the mass of the dish plus the rust, we're left with oxygen. So this would be C minus B. See the difference? You get the wrong letter in there, all your answers are going to be off. So the numerator here would be C minus B. And if we were solving for something else, or if we labeled these differently, this would be a different equation. So it's specific to each experiment and how you assign letters. Here we go. Now, do you see how this could be hard to do qualitatively? Because what if something, now you could probably, if an error occurred to A, you could figure it out in your head. So if something made A too small, you're subtracting a smaller number, which makes this bigger. Since it's the denominator, it would make the mass percent oxygen too small. If something affected B, right? So say something made B too larger than it should be. Well, you're subtracting a larger number, which makes it smaller, which would be the numerator smaller, which would make the percent mass oxygen lower than it should be. So you can analyze that. But for C, what if something happened to C? You don't know the sensitivity of the numerator and the denominator to changes in C. They don't necessarily cancel out. You just can't say, well, if C was bigger, it would cancel out proportionally. B and A are different. So the impact of the change in C is different in the numerator and the denominator. You can't predict that on the top of your head. You've got to calculate it quantitatively. You got to do it this way. I'm so sorry. All right, let's move on to step 5. Now that we've got it equated, that's the most important step. Now it's just a matter of let's plug in 30 for A, 50 for B, and 80 for C and see what we get. And that would be the value for the percent mass of oxygen, assuming a perfect experiment with no error. That's our baseline. Let's calculate our baseline. Did you calculate it? Did you calculate it? All right, let's calculate our baseline. Remember, the baseline is the value assuming no error, a perfect experiment theoretically. So we set up our equation for the percent mass of oxygen in rust as C minus B, the mass of the oxygen, over C minus A, the mass of the rust. Take that ratio times 100. Well, we assigned C, the largest value, 80. That was the empty dish plus the rust. We assigned a value for B, the mass of the empty dish plus the iron, a value of 50. And we assigned a value of A, the empty dish, evaporating dish, a value of 30 because we ranked them properly. So we're going to get 80 minus 50 in the numerator, 80 minus 30 in the denominator, times 100 to convert it to a percent. So 80 minus 50 is 30. 80 minus 30 is 50. So 30 divided by 50 times 100 gives us 60% by mass oxygen. That's not the true value. We don't even have actual data yet. We're just theoretically analyzing it. So what we're going to do in step 6 is I'll throw up maybe 2 or 3 different errors. We'll have to say, well, does that error affect A, B, or C? Or 2 of the 3 or all 3? Does it make them bigger or smaller than they should have been? And then we'll recalculate this and see if we get an answer bigger or smaller than 60%. If we get a value bigger than 60%, obviously that's B. We would get a value that's way too high. If we got a value lower than 60%, that would be smaller. That would be a value smaller than the true value. We'd put an S there. Right? Once you got this, it's a piece of cake. I can give you 100 different errors. Boom, 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 boom. So let's walk through just a few so you get a feel for it. Here's an error for you. Common one, especially if it's the end of the lab and you're in a hurry. Right? So you weighed the empty evaporation dish, you put the iron in it, weighed it. No problem, no errors there. But let's say you heated it up and formed rust, right? You added the oxygen from the air. And so your evaporation dish was warm. And you're running out of time, so you didn't let it cool at room temperature, so you went and waited on the balance while it was warm. That's going to give you a lower value. So we got to think, what error does this affect? This affects or impacts the dish plus the rust, right, which was C. Now, does it make it higher or smaller? Well, if you weigh something warm, it's lighter. So C is going to be smaller than it should be. So we normally said it was 80, right? So the mass of the iron plus the rust we assigned, the dish plus the rust we assigned is 80. So let's let C equal 70 instead of 80. 80 was if there was no air. We let it cool to room temperature. But let's say we were in a rush and we weighed it warm. Uh-oh, it's 70 now. Let's recalculate. Right? So now, let's recalculate our mass percent oxygen. Exact same equation, but we're going to plug in 70 instead of 80 for C. And see if we get a value equal to 60%, lower than 60%, or greater. Let's plug it in. So this will be 70, right? Well, we'll put it in C minus B over C minus A times 100. Exact same equation. So C is now 70, but no effect on B. We'll keep that as 50. C here becomes 70. No change on A. The mass of the empty dish was fine. Times 100. So let's get our trusty dusty calculator. I don't know what this is going to be. I'm just making this up as I go. We should be able to do this in our head, right? So 70 minus 50 is 20. 70 minus 30 is 40. Do we need a calculator? Can you see that's going to be 0.550%? So even though intuitively we would say, well, these change by the same amount, shouldn't they cancel out and have no effect? We should get 60%. No, the denominator and numerator have different sensitivities to that change. So this is lower than the baseline. So the effect, so the final value is small, or we could say S. We could say, hey, you're brainstorming with your friends saying, if we weighed this warm, would it cause our final mass percent oxygen to be bigger or smaller than the true value, or the same? Well, it would be smaller. See how that works out? Let's bang through one more real quick and we'll be done. Here's another error. I mean, you could brainstorm with other students, probably come up with at least 10 different things that could go wrong with this. Let's say when you, we're going to weigh the original evaporating dish, you sprayed it out with some DI water because you thought it was dirty, and you didn't let it dry out. You shook it out and you had a few drops of water on there. Didn't think about it, and you go and weigh it. Well, obviously, the measurement A is going to be bigger than it would be if you'd let it dry first, okay? So A is going to be heavier than it should have been. So A was normally 30, the empty evaporating dish, and we're assuming a dry one would be 30. So let's say it's 40 instead of 30. Let's recalculate. And what happens, though, is when you put the iron in and weigh it again, and then heat it. There's a couple assumptions, right? There's always a few assumptions. So you weigh it, and then you put the iron in, all right? So we got to make this assumption now. We can get two different answers here. Is it still wet, right, when you weigh the iron? Or did the water evaporate out? Depends how much time went on in between. See what I'm saying? So that could also affect B, the mass of the iron plus the dish. It would not affect C because you heated it. All right, you heated it and that water would be gone. So let's make the assumption, because otherwise we get two different answers. Let's make the assumption that the water was evaporated before you weighed the dish plus the iron. That would make a difference, right? So let's put here, dish plus the iron not affected. Let's say the water evaporated. Right? That's a little more complicated one. You got to make some assumptions. And based on your assumption, I would have to give you a grade based on your assumption. So this is what would happen, assuming that water had evaporated in the meantime. So here we go. Let's recalculate with a value of 40 instead of 30 for A. So take C minus B, 80 minus 50, both unaffected, over C minus A. C is unaffected, but now we're using 40 instead of 30. I left our baseline up there. So we get 30 over 40 instead of 30 over 50. Notice the denominator is smaller, so we get 75% over 60%. So that's bigger, right? So that error, weighing that dish wet, would create a value that's bigger than it should be. Now, you could, if you want to, we're out of time, if you didn't assume that, and let's say that the dish plus the iron was still wet, B would also be bigger, so you could let B, say, be 60 and recalculate. You're going to get a different answer. All right, quantitative. So you can do this. Just to get that equate. The key thing's the equation, and then whatever error it is, what measurements affected or more, could be one or more, and then just make them bigger, smaller, recalculate compared to the baseline. All right, you can do it. You can do it. Just get that equation and you can rock and roll.